announcement before Yoshi's talk. That tomorrow we'll have a group photo at 4:30 p.m. Okay, pode? So it's a great pleasure to introduce Yoshiharu Kohayakawa, who talk from Universidade de São Paulo, who talk about extremal problems for random discrete structures. So please, Yoshi.
So thank you very much to the organizers for inviting me to give a lecture here. It's a great pleasure. It's a great honor. Thank you very much for coming. Right. So I will speak about extremal problems for random discrete structures, and so the aim will be to discuss some results in a certain line of research in probabilistic combinatorics that I have been involved with for some time. And to be more precise, what I want to discuss is the following. So I will be interested in probabilistic versions of certain extremal results in combinatorics, and by extremal results I mean density results. So partition results would fit also to this talk, but to focus on one, kind of try to focus, we'll just discuss density results. And also we could discuss probabilistic, so what I mean by this research, we will be interested in probabilistic environments. It also would make sense to talk about pseudo-random environments, but I will again omit this other possibility, and I will focus on probabilistic environments. Okay, so the outline of the talk is as follows. So there will be a fairly long introduction. So I'll talk about graphs, hypergraphs, and sets of integers. Well, just define the objects and my notation. Then I will talk about classical extremal results for graphs for some time. And among those, I would like to discuss what is known as degenerate extremal problems. And then I will very briefly say what I mean by random graphs. And then I will discuss threshold functions, because they will be very important in the main part of the talk, namely when I talk about probabilistic versions of classical extremal results. So in this here, I would like to kind of try to mix together the previous deterministic and probabilistic setups. And towards the end, I will try to talk about degenerate extremal problems in this probabilistic context, in which there is some phenomenon which I find quite interesting, and I will give as an example some concrete theorems about Sidon sets in random subsets of integers. Okay, so this is the plan. So let me start with this introduction, which is, I apologize, is fairly long, but I hope it will be useful to some, and I hope it will not send others to sleep. So let me see. So graphs, so there's nothing surprising here. So a graph will be just a vertex set and edge set, VE. Nothing unexpected. Now for hypergraphs, when I say hypergraphs, I mean uniform hypergraphs. So a K-uniform hypergraph is a pair, V, E, where V is a set of vertices, and the hyperedges, or edges maybe simply, is just a collection of unordered K-tuples of vertices. So when K equals 2, I just mean graphs. K equals 2 is the same as graphs. Actually, hypergraphs won't show up so much in the lecture. So this is two particular hypergraphs, so F1 and F2. So there's 3 in parentheses on the top, kind of is often used to indicate that you're talking about a hypergraph which is 3 uniform. So the hyperedges have 3 elements. So in F1 you have 3 hyperedges, a blue one, a red one, and a green one. F2 has 2 hyperedges, 2 triples, 1 blue and 1 red. And actually maybe this would be a better kind of drawing of those, but anyway. Okay, so these are just so that we know what we're talking about when we talk about hypergraphs. So these are triple systems or 3 uniform hypergraphs. And, well, okay, for integers. So for us, the integers, we will be concerned with the initial segment of the positive integers. So I will denote that by brackets n. So these are the first n integers. And when we talk about extremal problems for integers, we will be interested in subsets of brackets n. So this could be some subset A of the integers that we are interested in. And a typical question you can ask here is whether this set A contains 4 elements in an arithmetic progression, so equally spaced integers. So this is AP4 inside the set A. AP4 is a 4-term arithmetic progression. Okay, so now we know what the objects are. We know some of the notation. I hope I've introduced the basic notation. Let me start talking about classical extremal graph theory now. So this is an area which is very active, but perhaps the first result in this area is Mantels Theorem. It's actually kind of an isolated result which appeared in 1907, and then kind of nothing happened for some time, but this is maybe really the first result in the subject. So the theorem, Montell's theorem, says the following. So any graph G on n vertices with more than this many edges must contain a triangle. And a triangle is, well, my notation for triangle is K3. It's just 3 mutually adjacent vertices. Okay, so again, and this number n choose 2 times n choose 2, once rounded down and once rounded up, is a very easy number to understand. So it's this. So we are talking about a graph on n points. So if you have n vertices, you can split that into 2. If it's odd, then maybe you have to do this, right? And then you consider all possible edges here. And of course, if you do that, you get that number. And of course, in here, you do not have this object which we are forbidding, namely 3 mutually adjacent points, right? So this thing doesn't occur in this graph. And the theorem says that if you have one more edge than this graph here, then you must contain 3 mutually adjacent points. So a K3. Okay, so my notation for this extremal function x and f, so what is the extremal problem involved here? So it's like this. So you fix the number of vertices. So this is, you say, I'm interested in graphs on n points. And I also have some forbidden subgraph, in this case, f. And I would like to maximize the number of edges of G, right? So this is the basic extremal function we are interested in. And Mantell's theorem just says that this quantity is precisely this. This x of nk3 is precisely n over 2 times n over 2, round up, round down. Okay, very good. So this is a precise result for triangles. But let me give a slightly less precise version, which perhaps, yeah, so this will be important. So let me define this notion of density threshold. I'll write here because there will be one more kind of threshold so that we don't mix them up. So I will try to, so density threshold. So this is one kind of threshold that we'll be interested in. So Mantell's theorem tells us that the density threshold for triangles is 1/2, by which I mean the following. If you have a graph on n points and you take some subgraph of, yes, you have n is a fixed parameter, large number of vertices. And now you consider a graph G which has density a little bit more than 1/2, so 1/2 plus epsilon for some positive epsilon. Then the conclusion, the Mantell's theorem implies that this must contain a triangle. So this graph has density precisely 1/2, and if you go some small percentage about 1/2, then you must have a triangle because of Mantell's theorem. Or if you like, if you write this expression, this extremal function in this form, so some coefficient times n choose 2. N choose 2 is how many edges you could have on n points. then the coefficient here for triangle is 1/2. So that is what I mean by density threshold, is this coefficient when you write this x function as constant times n choose 2. Okay. I said the same thing in 3 different ways, but I hope, right. Just make sure this density threshold notion will be important. So this is another isolated result in classical extremal graph theory. And this is, so this appears in a paper by Erdős from 1938. So his question, he was interested in this question, among others, in this paper. So what is the maximal number of a multiplicative Sidon set S contained in brackets n? So multiplicative Sidon means just this. It means that if you take pairwise products of members of S, then you get different things. Or in other words, if you take x, y, w, z in your set S and you multiply and you get equal, then it must have been because you chose actually the same pair. So all the pairwise products should be different. So that is the definition of a multiplicative Sidon set, and the question is how big such a set can be as a function of n. So one example of a multiplicative Sidon set are the primes. You could take the primes within brackets n, you get such a set, right? And it's kind of surprising that actually you cannot get much more than that. You get the primes plus a little bit. And it even turns out that this error here in this paper is proved to be already close to sharp, because he gives a construction which differs by n to the 3/4 just by a factor of log. Anyway, so he was interested in this combinatorial number theoretic question, and to do this, so he says, well, so he has some argument, which we will not discuss, but he says later on in the paper that actually the argument was really based upon the following theorem for graphs. So let 2 k points be given. We split them into 2 classes each containing k of them. These two, the points in the classes are connected by segments or edges. And you have one condition. The condition is that there should be no closed quadrilateral. So he's saying if you have k points, and then so he has some edges. And what is forbidden here is to have this configuration here. It's mixed up, but it's kind of this, right? Which now perhaps one could call a cycle of length 4 or closed quadrilateral, as he called. Okay, so how many edges can you have without this? So that was the problem that a lemma that he had to solve, and a problem that he had to solve. And his lemma says that such a graph has at most 3 times k 3/2 edges. So number of edges here. So no, then implies number of edges is at most 3. Okay, so this is the combinatorial lemma extremal problem that he had to solve to address his multiplicative Sidon set problem. Okay, this is kind of, again, some considered to be an isolated result in the area. This, but of course the pattern is clear, and Turan was the person who really started the systematic study of this, and he asked the question for general complete graphs on q plus 1 points. So Mantels Theorem was the case q equals 2. So Turan asked what happens if you forbid q plus 1 mutually adjacent points. How many edges can you have if you have n vertices? And so he gave a precise answer, and the answer, to say the answer, let's consider this graph, T and Q. So this graph is like this. You split, you have n vertices. You split the n vertices into 1, 2, q parts, you make all the sets of the same size, so n divided by q. Of course, yeah, so if n is not divisible, then some of them will have one more than the others, but you split them as equally as possible, and you put all edges across, right? The only thing you don't do, I mean, the only forbidden edges are the edges which are inside each class. So those are not in the graph. Okay, and well, clearly this guy does not contain q plus 1 mutually adjacent points because there are only q parts here. Okay, and so what I just said, the fact that this graph is not contained here, shows that this function is at least as large as this. Well, the little e means number of edges here. And Thuram's theorem says that this is actually the correct bound. This is a sharp bound. Namely, this graph maximizes the number of edges in a q plus 1 free graph on endpoints. And this is very nicely generalizes Mantels Theorem, which is that, right? Okay, so for triangles, the density threshold was 1/2. The density threshold for this case is given by this T graph, and actually this quantity is 1 minus 1 over q. So just a sanity check for q equals 2, you get half, right? So, but for this general case, it's 1 minus 1 over q. This graph has density 1 minus 1 over q. So the only forbidden edges are inside, and random pair falls inside with probability 1 over q, if you like. Okay, so this graph has density 1 minus 1 over q, and that is the density threshold for q plus 1 mutually adjacent points. Now we should go on, and we should ask what happens for arbitrary graphs, so general graphs f, right? And then there is a very nice theorem for this case. So let f be an arbitrary graph with at least one edge to avoid trivialities. So let's start with a lower bound. And the lower bound is, again, you just, it's very nice. You just take this construction and you adapt it. So, right. So one defines this quantity chi of f. So in graph theory, this is known as the chromatic number of this graph f. And with the notation we have so far, we can simply say that this number is the smallest q for which f is contained is a subgraph of this graph tq and infinity on the top. So you think of this graph, you think of a tqn with n very big with respect to the graph f, and you try to embed f into this. And the smallest q for which you can do this is this parameter. So now you want to do this, right? And this chi of f is mean q for which this is, one can do this. And you put some large number here. You put some large number here so that the only reason this wouldn't embed is combinatorial and not because you don't have enough vertices. Right, so you put here number of vertices of f, if you like. Anyway, so this is the chromatic number of the graph f. And clearly, if you, by this definition, if you put a number here which is 1 less, right, tn chi f minus 1, then by definition, f does not embed into this t graph. And therefore, this is a lower bound for this extremal function. And we have already observed that the density of this graph is this 1 minus 1 over chi f minus 1 is 1 minus 1 over the lower index. And the very nice theorem of, this is known as the Erdős-Stone-Simonovic theorem, is that this extremal function x of nf is actually given by this. So this is this gives the best lower bound. I mean, this is a sharp lower bound. This extremal function, sometimes called the Turan number, is just determined by this chromatic number chi of f.
So what's the difference between these two results?
Okay, so this is just a lower bound. We just said, okay, so if I want to avoid f, one thing I could do is to do this construction. And the bottom theorem is the upper bound. So this means that if I take a graph which has 1% more edges than this guy, then you must have f. Right, so, yeah. Yes, okay, so Erdős-Stone-Szymonovich is, yeah, it's this upper bound. Right. Yeah, so it's 2 because, yeah, anyway. So it's 2 papers because Erdős and Stone proved this for large, complete p-partite graphs, and never mind. So, yeah, it's known as the Erdős-Stone-Szymonovich theorem. Yeah, but I hope the statement is clear. So this is a simple construction, lower bound, and this says if you go just 1% above it, then you will force f in your graph G, which of course could be completely different from this, right? But if you have just 1% more edges than this, then you force your forbidden graph f. So again, the density threshold for the graph f, for an arbitrary graph f, is given by this quantity, 1 minus 1 over chromatic number minus 1. Okay. So this is very nice because for an arbitrary graph, you know what the density threshold is. Now let's move on to these degenerate extremal problems. And by that I mean, so this is based on the following observation. So this quantity, 1 minus 1 over chi f minus 1, of course it's 0 when chi of f is 2. So for instance, this C4, this closed quadrilateral or 4-cycle, embeds into this graph here, or if you like, or perhaps embeds into this graph here. This is the graph which I previously called Tn2. So the chromatic number of this is 2. Yeah, it's a bipartite graph in the language of graph theory. Okay, so for this graph, C4, this Erdős-Stone-Szymonovich, or actually previous results, actually imply, only imply, or so let me start again. So this Erdős-Stone-Szymonovich, as I stated, implies that this function is little of n squared. But again, yes. Well, actually, for this maybe for just what I said, it's just little n squared. Now, but of course you can add, so that is actually the main point. So, but you want to say something more than this, and I will say something now that will tell us something about this exponent. Right? Okay, so if you only say that in my language, so if I say that the density threshold is 0, we are only saying this. And of course, you would like to know more. And if you remember this Erdős's paper from 38, so he got some explicit bound for this function. Actually, this is, in my notation, something close to this. It's not exactly, but it's rough. It's basically the same. So if you have a graph on n points and you want to avoid a 4-cycle, closed quadrilateral, you cannot have more than n to the 3/2 edges up to constant. And this was actually important, so this actual function was important for him to get these 3/4 here. So my only point is that when you talk about the degenerate problems, namely problems for which the density threshold is 0, in the case of graphs, actually, you know exactly when this happens, right? This happens precisely, so density threshold is 0, precisely when this function is little n squared, precisely when the graph is bipartite. So, right. So you know precisely what, in the case of graphs, what that is. Of course, it makes sense to ask a finer question. So how much is this function? So you would like to prove maybe it's n to some exponent. with some exponent less than 2, so that is what you asked, right? And actually, so this question is formulated this way because of some old result, one of the classical results in the area, this Kovaresh-Shor-Sturan theorem, that says that for this guy here, KAB, you have this bound for the extremal function. And this KAB is the graph that you have. You take A points here, B points here, and you put all edges. Complete bipartite graph on A points on one side and B on the other. So you can prove this bound for this graph. Okay, so it's an exponent strictly less than 2 for these guys. So for any bipartite graph, you will have such a thing. So for this, so here, for instance, this implies that for C4, you get this n to the 3 halves because A equals B equals 2. Okay, very good. So this is the more kind of, this is the question, right, for the degenerate case. And, but so that you see that it seems to be a difficult problem, so there are some results here. So this upper bound is known to be sharp for B at most 3. These are kind of from the mid-60s. But and this was kind of for a long time the only case in which it was known that this is sharp. So it's only in the 90s that it was proved to be sharp for some other general family or general case. So when B is quite a bit bigger than A, then there are some algebraic constructions that prove that this bound is sharp. So it seems, so even for this simple bipartite graph, it's still unknown what this function is. Okay, and but now to illustrate that this area seems to be very rich, or the results perhaps can be quite complicated, or so there is this conjecture of Erdős and Simonovic, known as the rational exponents conjecture. The conjecture says that for any graph f, actually this function x of nf is of the form n to the alpha, up to some, so constant times n to the alpha, and alpha is some rational. Of course, the kind of interesting case is when f is bipartite, so it embeds into one of those guys, and alpha then is strictly less than 2. But anyway, so to have this whole range for any so if you have any bipartite graph, then it's expected that the extremal function is of the form n to the alpha, constant times n to the alpha. There's even some kind of inverse conjecture that says that for any alpha, there is some bipartite graph for which this extremal function is at least up to the multiplicative constant n to the alpha for that given alpha. So this seems to show that the range of answers that you can have, or this extremal problem can have a wide range of answers, right? So anyway, so this was what I wanted to say about the degenerate problems for graphs. We'll come back to this later on when I'm talking about these probabilistic versions of such things. This is just a way of kind of introducing the next topic. Let's remark that for graphs, it's very easy to identify the degenerate cases, but sometimes in some other contexts, even proving that some problem is degenerate, namely that the density threshold is 0, is a tough problem. So for instance, so here's what I say. So sometimes proving that the density is 0 is very difficult. And of course, Civilities Theorem is actually like that, right? So if your forbidden configuration are arithmetic progressions on k elements, so in my notation maybe this would be to study this function. The theorem, namely to prove that this quantity is little o n, that's a degenerate case. It's Civilities Theorem, which is well known to be a hard theorem. So again, I'm still, I will state it because, it's probably unnecessary, but I state Semiramis theorem. So the classical notation is Rk of n. So k is some fixed integer. Your forbidden objects are k-term arithmetic progressions. You want to know the maximum size of a set S containing brackets n with no APKs. And Semiramis theorem is that this quantity is little o of n. Or in full for any k and for any epsilon, if you take large n, then this Rk of n is at most epsilon times n, right? So this only says that the density, in my kind of language, I'm saying that the density thresholds for APKs is 0. So this is proving that it's zeros can be difficult. And of course, you all, or vast majority of you, know that there are several approaches to this Semiramis theorem. And I will just say just one slide about fully combinatorial one based on hypergraph density results. So far I've been talking about this X function, and I'm kind of trying to sell you that this X function is interesting. So I just wanted to mention one very interesting line of research in which one links these two things. So there's a very close relation between extremal hypergraph problems and Semiramis theorem. And this goes as follows. So this was already known to Rouget and Semiramis for k equals 3, for the first non-trivial case, arithmetic progressions on 3 elements. Now, but you can generalize this to general k. So there's this X function here that we have been considering. And I put two hypergraphs, k uniform hypergraphs here as the forbidden objects. But if I do that, proving that this X function, by the way, I'm not telling you what this F1 and F2 are. So I'm just saying that there is F1 and F2. And I'm just saying that this X function, proving that this X function is little of n to the k minus 1, actually implies Semiramis theorem. So this Turan type problem, this density problem for hypergraphs, kind of can encode Semiramis theorem. For k equals 3, these are the two hypergraphs that we had at the beginning when I was defining hypergraphs. But anyway, so this implication is interesting. And what is also very interesting is that one can, in fact, prove this necessary hypothesis for this implication and thus prove Semiramis theorem via an extremal problem for hypergraphs. And this was done by generalizing greatly this method of Semiramis of regularity, so the regularity lemma of Semiramis to hypergraphs. And this was done by Frankel and Rodel for k equals 4 first, and then Rodel and co-authors and Gowers. And then there's some subsequent work by Tao and Elek and Segedi, which are very interesting. But so we don't move into this direction. I will now go to the probabilistic part of the talk. So far everything has been deterministic. Now I'd like to talk about random graphs. And for random graphs, so historically, Erdős and Rainey wrote papers in 59 and 60 in which they started the investigation of random graphs in a systematic way. And so the theory of random graphs today, kind of the way it's done today, is associated with these two papers. So it was born with these two papers. Now, let me say what the Erdős-Rainey model is. So I will write G and M for this random graph of Erdős and Rainey. N is the number of vertices, as before. And M will be the number of edges that I will have in this graph. So M is usually some function of N. So I don't know, it could be half times N choose 2. And G and M is simply a graph on a fixed set of vertices, let's say brackets N, with M edges. And of course you have N choose 2, choose M, such graphs. You just sample one uniformly at random. So this GNM is just a uniform random graph. All the graphs are equiprobable with these two parameters, n and m. Okay, this is GNM. So it's a uniform model on this space here. Now, so among others, one nice discovery of Erdős and Rényi are these threshold functions. So let me define them. So we define this in a pretty general way. So we start with some property of graphs. So this is just a subset of graphs which are closed under isomorphism. So given a graph, given the isomorphism type of a graph, I can decide whether this property is true or not. Yeah, okay, anyway, so I have a property of graphs. So for instance, and I want it to be monotone increasing. That means that if a graph has this property, then any supergraph of it has it. And here, by a supergraph, I mean, in this context, I just mean you're allowed to add edges. You're not allowed to add vertices, right? So, for instance, if a graph contains three mutually adjacent points, okay, three a triangle, then if I add an edge, of course, this triangle is still there. You don't destroy it. Being connected is also a monotone increasing property in here, because I don't allow to add new vertices or new edges. So you have this fixed set of vertices and you add edges. So this is a monotone. So being connected is a monotone increasing property. Okay, for such a property, a threshold function m star is a function that has the following property. We consider this random graph GNM, and we check whether it has P or not. Actually, we're interested in the limiting probability that this random graph has P when we send n to infinity. And of course, here the point is, what is m, right? So for this m star to be a threshold function, we require the following about this limiting probability. If you put some function m, which is asymptotically smaller than m star, this limit has to be 0. And if you put some function m here, which is asymptotically bigger than m star, then this limiting probability has to be 1. If you have these two conditions, then you say that m star is a threshold function for this property P. And Erdős and Rényi proved that there are very natural graph theoretical properties that have threshold functions. So, yeah, so for instance, for K3, which is a threshold function, it turns out to be n. For 4 mutually adjacent points, K4, the function is n to the 4/3. So they proved a more general theorem about such things. They also addressed the question of connectedness, and they proved that n log n is a threshold for this property. So if you have asymptotically more edges than n log n, your graph will have probability 1 of being connected, or approaching 1 of being connected. And if it's asymptotically less than n log n, then the probability is 0. Actually, there are much more precise results for this connectedness, but let's not talk about that. Okay, so this is the concept of threshold functions. And it's, right, so it's quite surprising that several natural graph theoretical properties admit threshold functions, but there is some abstract theorem that says that every non-trivial monotone increasing property must have a threshold function. Okay, so that's good. So if you have monotone increasing properties, there is a well-defined threshold. Right, so this is what I want to say about random graphs. So we have kind of gone over the long introduction. Now I would like to say what I mean by these probabilistic versions of extremal results. So we're going to kind of put all of this together. So probabilistic versions of Turan type results. So let's recall Mantels Theorem tells us that the threshold for triangles is 1/2, right? So if you have 50.0001% of edges on n points, then you must have a triangle if n is big. So you can ask whether such a property is true for arbitrary graphs. So this means, so I will write this arrow notation. If any, so there's this half plus eta here. this numerical parameter. So if any half plus eta fraction of the edges of this graph G gives me K3, generates K3, or spans K3, then I will say that this graph G has the eta Montell property. So eta is here. And if you like, Mantels Theorem says that large complete graphs have the Montell property for any eta. So to be more precise, for every eta there is, if n is large enough, the complete graph on endpoints has this Montell property. Okay? So, right. So you have this property of graphs, this property of graphs. For every eta I have some property of graphs. It makes sense to ask whether this has a, what is the threshold function for this? Yeah, so we have this density threshold. I said there would be some other threshold, and maybe I can call this Erdős-Rényi threshold. So this is that M star that appeared before, right? Okay, so you can ask whether this, what is the Erdős-Rényi threshold for this graph property P Montell eta? So that's kind of the question. So I've been working hard to try to convince you that this is a natural question. Actually, this property is not precisely monotone increasing, but it's stochastically increasing. But anyway, so I hope with this introduction, I hope you believe that it's kind of natural to ask what the threshold is. And in fact, this was answered long ago by Frankel and Rödl. The threshold for this property is n to the 3 halves for any fixed eta. For any fixed eta here, this threshold is n to the 3 halves. Or if you like, eta only kind of affects the coefficient of this function. Anyway, so this was solved long ago. And in fact, this problem was addressed by Frankel and Rödl because of a certain problem by Erdős and Neshatril. So I've been trying to say that determining the threshold of this property is a natural problem, but actually Frankel and Rödl wanted to solve a problem of Erdős and Neshatril. And the problem is as follows. We are interested in this Montell property. So you want to say 51% of the edges of the graph implies triangle. So, and if you have a complete graph, this is true by Mantels Theorem. But then you can impose some condition on the graph, which kind of goes against it. So for instance, suppose that you forbid K4. So you don't want to have 4 mutually adjacent points in your graph, but you still want it to be very triangle rich, so that when you take 51% of its edges, you do get a triangle. So this was the question of Erdős and Neshatril. Are there such graphs for any eta? And the answer is yes. So Frankel and Rödl solution to this problem was based on random graphs and was based on the fact that if you take this graph here, so remember n to the 3 halves I stated before is the threshold, so they proved this. And the fact is that if you take this random graph and you kind of do some little thing with it, so you just remove some edges from it, you do some small perturbation, then you will obtain a graph whose existence was asked by Erdős and Neshatril. So the problem itself of determining thresholds, this Erdős-Rényi thresholds or probability thresholds, I believe is interesting given the theory, past history, but you can also find applications. Let me just comment that, so it's not, so for instance, you can ask, so how small such a graph G can be? Are there other constructions not based on random graphs? And this is kind of quite interesting. So I'm not, so for instance, I believe, I believe there are graphs, it's known that there are graphs on fewer than 1,000 vertices that satisfy, that answer this Erdős-Neshatril problem. Yeah, maybe, no, let me not talk about that. Yeah, so anyway, so there are no really simple constructions for this problem. For a related problem, related to partition rather than density, it's known, for instance, that there are graphs on fewer than 1,000 vertices doing this, but it's kind of hard work to prove such a thing. Anyway, so let me move on. So that was about triangles, and which is the theme of Mantels Theorem. But then we know that Turan kind of contains Montell, and in some sense, or at least in this density threshold sense, this Erdős-Stone-Szymonovich generalizes Turan's theorem. So you can ask, what is the, so this is again the Erdős-Stone-Szymonovich theorem. It says that in this arrow notation, if you take some little eta more than this pi f fraction of the edges of the complete graph on endpoints, then you must generate f, as long as n is large enough with respect to eta. So this is Erdős-Stone-Szymonovich. So the natural question is to ask the Erdős-Rényi threshold for this. And this was some problem which was investigated from the mid-90s for some time. And one could establish this for some, one could prove a certain natural conjecture for cycles and complete graphs. But for general graphs F, this was elusive. One could prove some weaker bounds for the threshold for arbitrary F. And this was all based on regularity. So this was based on the regularity lemma, or some way, or generalizing the regularity lemma for this context. And to those for which this is not too familiar, perhaps it's more familiar to say that this is this decomposition structure, pseudo-randomness decomposition method. But anyway, so it was kind of very nice that a few years back this was solved. So the natural conjecture was actually established independently by Schacht and Colon and Gauss. So for any graph F, the threshold for this property here is known. And I will not discuss, given the time, precisely what this threshold is. It's actually it's given by some kind of density. Let me only say that, there's even a typo. So if you want to know the threshold for this function, for this property, so this should be F. So what you do is to compute some kind of density. This is number of edges divided by number of vertices somehow. So this is kind of a notion of density, which I will not go into.
What is the delta F?
Yes, delta F. Yeah, right. There is something that, to exclude some trivialities, you have to impose that there are no isolated vertices, okay, but you have no vertex which is incident to only one edge. So you require every vertex to be incident to at least two edges in this graph F. It's some non-triviality condition. It's not so important. Okay, let me see. So so this is some discussion about why this should be the threshold, but I will skip that. It just wouldn't be fair not to mention a predecessor theorem. So there's a corresponding theorem to this, which relates to the partition version of the problem. And this was done by Rodel and Bruczynski in '95. But let me move on. Let me just say that Schacht and Colon and Gauss had quite different approaches to this. One is kind of more combinatorial and the other more analytic. And in fact, they proved some general transference principles which allow them to take some extremal problems, some density problem, or also partition problems, and they could kind of sparsify them to random sub-environments. So it's more an abstract theorem, out of which they could deduce several results in different areas, so additive combinatorics for graphs and hypergraphs. So for instance, for similarity, their theorem is as follows. So the probabilistic model here is like this. So we have brackets n, this is the universe, and we will sparsify it randomly. So we take an m element subset of brackets n, uniformly at random. So we have some function m of n, so m could be root n or n to the 2/3, and you take a subset of n considering all n choose m subsets equally likely. And for this random set, you can ask whether this has the similarity property, namely any eta fraction of this set. Is it true that any eta fraction of this set contains a k-element arithmetic progression? So is it true that the density threshold for APKs in this for this random object is 0? And the answer is yes, it is, as long as you have this function, as long as you don't take m to be too small. If n is at least this big, then the APK problem, the similarity problem, is a degenerate problem. And so, yeah, so we had this for 3, but proving for general K looked like a very difficult, yeah, it was difficult for us. And it looked like one had to invent more about regularity for hypergraphs. But they actually could do in a different way. So they, let me say, they bypassed this regularity method. They did it some other way. But now it's actually, but actually this regularity method has been kind of now successfully generalized for this random sparse setting, thanks to the work of several people. So Balog, Rob Morris, Wojtek Samoti, David Saxton, and Andrew Thomason, and then also Colin Gowers, Samoti, and Schacht. So there is, so I think it's fair to say that there is some kind of very nice, powerful generalization of this regularity method for random environments. But this is, let me not go into that. So I just want to use 2 minutes, 3 minutes to talk about degenerate problems. And so here, let me see. I will be interested in the following. So let me discuss this blue row here. So when you say that the problem of the extremal problem for 4 cycles, it is, so we're going back to Erdős 38 paper, right? So saying that this problem is a degenerate problem, it's good. It's definitely some interesting information, piece of information. But saying that this function is n to the 3 halves, well, that's more interesting, right? And in a way, and in a way, these results by Schacht and Colin and Gowers and others say a lot about these probabilistic versions of these extremal problems. But in the degenerate case, one can ask more. So one can kind of try to ask this question, whether one can prove such sharper results. And now I would like to say just a few words about that in one concrete case. So the case, I would like to talk about B2 sets or Sidon sets. So one says that set S is a B2 or a Sidon set if you have no non-trivial solution to this equation. Or if you like, if you take all pairwise sums, they're all different. So if you compute A plus B with A and B in S, they're all different, right? Okay. Now, it's some classical result from the 40s that the maximal size of such a set inside brackets n is root n. So it's a very degenerate problem. Okay? So it's a degenerate problem. So any positive eta that you put here, you kind of imply, you force a non-trivial solution to x plus y equals w plus z. And so we could say that a set A has a eta Sidon property if this is true. Any eta fraction gives you a non-trivial solution to this equation. Okay, so given some property, you can ask, so that is the game we've been playing, so you can ask what the Erdős-Rényi threshold, so this m star function, is for this Sidon property. And, okay, I'm sorry, so I'll just state it. So if you kind of read this, read out from the theorems of Schacht and Colin and Gowers, it's clear that n to the 1/3 is the threshold for this problem. But then we want to ask kind of more. We want to write something stronger than this. So not only little o m on the right-hand side, we want to say something more, right? And Let me not say why. Okay. I think it's, yeah, so I hope it's you'll find it a natural problem given past history, but you can also kind of solve problems similar to this or analogous to this Erdős-Nestor problem that we discussed when we talked about the case of triangles and K-force. So I think it's fair to say that there are interesting corollaries of determining this threshold and studying this problem more. And now I will just state the theorem. The theorem is as follows. So suppose you take a set M, a subset, an M-element subset of brackets N with M n to the A, and A is some fixed constant. Then there is some B, which depends only on A, such that with high probability, this function, this extremal quantity is n to the B. And B is this piecewise linear function. So let me explain this in this graph. So we have brackets n, that's our universe, and we now take a random subset of size m. So this random subset of size m contains some Sidon sets, and we want to know what is the biggest Sidon set it contains. And the size of this Sidon set is n to the b. And this n and b kind of behaves this way. So up to kind of this part of the graph is if you decode what I'm talking about, it's very easy to see. And the fact that there is some discontinuity or phase transition here kind of follows from the theorems of Coulomb and Gauss and Schacht. But then the fact that this is completely flat here, it's kind of interesting. So you see, you take m to be, it could be n to 1/2 or n to the 2/3 or close to n to the 2/3. The biggest Sidon set you can find inside is still cube root n. And then at this point it kind of picks up and it grows, B grows linearly with A. So this is some interesting kind of unexpected behavior. Right. I will just say one thing. So there are some slides with the precise statements of these theorems. Let me only say the following. So here in the middle, the function, this function, is actually something like cube root of n log n. So there is this f function is like this in this middle interval here. And it's interesting that you get kind of this extra log. So it's not a rational exponent type of thing. There is some extra log. But let's skip those. And finally, there is a natural generalization, which is to talk about such a set. This is another, so such an equation. If you have no solutions to such an equation, you call the set B3. And you can ask the same. And so, yeah, I'm sorry, in the previous theorem I didn't mention my co-authors. So in the previous was with Lee, Rodel, and Samoti, and now with De La Monica. We kind of get a similar graph. So let me just show you the graph. We have this lower bound, and we have an upper bound. So they don't match from 2/5 to 3/4. We still don't know. We believe we know that the lower bound is sharp, but this is still in the process of being checked. So, okay, so I believe, yeah, we believe that the lower bound is the correct answer to this problem. Okay, so let me finish. I've already, yeah, sorry. So, so it seems interesting that these degenerate problems, one can kind of study the whole range, and you get this unexpected behavior. Well, thank you very much for listening. I'll stop here.